Recording is rolling. Welcome to Wednesday, April 19th. So we're going to do a Kahoot on relativity, some conceptual questions. A bunch of guys just hopped on that, about to switch over and do that. Okay. And, so I mentioned too, I have not printed these questions out, but I have posted them to Google Classroom. So if you want to access them there. Okay. So I'm going to see if you guys been able to follow the concepts of how special relativity works for the last couple days. Okay. And then the second half of class, we're going to finish these puzzles. You guys remember these puzzles from yesterday? We did about half of them yesterday. We're going to do the other half today. Okay. So if you guys have this paper on hand, who was not here yesterday needs this paper? Okay. Give that to you. Here, flip my screen over. You guys can finish hopping on Kahoot. Get you this paper. Yeah. All right. Who else needs this paper from yesterday? Paper from yesterday. Okay, so everybody's got this page from yesterday. All right, which we will finish there. All right, share my screen. Screen to share. All right, yeah, thank you everybody for hopping on. All right. And let's go. In contrast to an object with mass, no matter how fast the source of light is moving, light always there you go, has the same speed, right? The speed of light. Of course, we're talking about like through a vacuum situation, right? So remember I was saying, like, even if you were in a vehicle that was traveling at like half the speed of light, you turn on your headlights, right? Everybody, regardless of the frame of reference, if you're in the vehicle or outside the vehicle watching it fly by, right, everybody agrees that the speed of the light of those light beams is the speed of light. Yeah. So really, that's Einstein relativity. Einstein reasoned that there you go. Yeah, all the statements are true. Great. So all motion is relative, hence relativity. It's the root of that word. Right? You can't measure your speed relative to empty space. You can only measure your speed relative to something else, other objects, nearby planets if you're in a ship like flying through. I've seen a version of this. There's no such thing as a signpost of like the center of the universe. There's no such thing as the center of the universe, right? Or you could say the center of the universe is everywhere. It has to do with like cosmological expansion. Yeah. So all motion is relative. All right. Spaceship moves away from a station at half the speed of light. A person in the station flashes a light beacon. People in the ship will see the light traveling toward them at a speed of what? The speed of light. Right? Remember, the speed of light is always the speed of light, regardless of your reference frame. Right, let me switch over and draw this out. Right? So if you look at your notes from last couple of days, we've gone over some similar type examples to this, but we draw this exact scenario. Right? So let's say there's a planet here. On this planet, there's a station. Right? And it's sending out some signal. Right? And then a ship flies by at half the speed of light. So here comes this rocket ship flying by at, I'm going to say the ship is 1/2 c, half the speed of light. Right? Well, how about these light beams, like maybe like radio light waves or something, for example, right? That could be electromagnetic waves. Right? Well, these waves are traveling at the speed of light. Say the beam equals c. Right? Now, if you're here by the station, then of course the waves are traveling out at the speed of light. Right? Well, what if you're in the ship traveling at half the speed of light and the waves are headed towards you? What do you perceive? Well, you still perceive the speed of light. Right? Now, remember, this is not how Newtonian mechanics works. Right? Newtonian mechanics, maybe you could be throwing around a baseball and you say, well, it must be like the speed of light minus half the speed of light. Or it must be c minus one half c would be one half c, right? That's what you would think if you're in Newtonian mechanics, like throwing a baseball around, right? But no. With light, everybody always perceives the speed of light to be the same value, okay? No matter your own frame of reference. Yeah. All right. Next. All right. Got Cat on fire in the lead. Suppose we observe a spaceship whizzing past us at very high speed. Compared to what the person in the spaceship sees, we see that spaceship clock is running what? Sounds like the twin paradox. Right? Yeah, all right, nice. All right, so once everybody got that, let me switch over and just draw this one out just to emphasize this. Yeah, you guys remember twin paradox, right? Twin paradox, right? So we got Earth twin and rocket twin. They both start out on Earth. So they're both wearing a wristwatch. It's beating 1 second per second. That's all fine and good, right? Then, right, rocket twin takes off in a rocket, flies close to the speed of light. Right? Let's have Earth twin down here, and he's got a telescope, right? So he's looking at his twin brother's spaceship, right? So he's got a telescope, right? And let's get a blown up picture of this rocket. Right, so we're looking at the rocket. It's got a huge rocket window, right? Oh, and here's his twin brother. Yay, I'll find it good. And his twin brother has a clock on the wall. Right, we're looking at this clock, right? And Earth's twin down here, right? Like his own clock. Right? Maybe he's got his own clock here. It's going like tick, 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 like 1 second per second. So I'll find it good. But he's looking at rocket twin's clock, and it's going something like this: tick, 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 tick. It's beating way too slow. Remember when rocket twin returns to Earth? Earth twin it has aged a lot, and rocket twin says, no, barely any time's gone by at all. Right? You guys know that? Right. So that's there's your time dilation, and the expression that backs this up is this time dilation right here. Right? So rocket twin's time compared to Earth twin's time. Right? This Lorentz factor, this whole square root, is bounded between 0 and 1. So if rocket twin says like an hour's gone by, if you divide by something between 0 and 1, because if you divide by something between 0 and 1, does that make the number bigger or smaller? What is 1 divided by 0.3? Ooh, like 3 point something, right? So maybe rocket twin says 1 hour's gone by, but Earth twin says 3 hours have gone by. Ooh, right? So rocket twin's clock appears to be running slow. Again, that's only from Earth twin's frame of reference. You have to be looking through the telescope for that to happen, right? You guys got that? Yeah, most you got that. So awesome. All right. Got Ade, Stephen, Fred, and Hoot. If you're on a high-speed spaceship relative to Earth, you would yeah, you would not notice anything strange, right? Oh, remember, all these relativistic effects are only from like different frames of reference, right? If you're along for the ride with Rocket Twin, you don't notice any weird time dilations. Look at the clock on your own wall and say, no, it's still beating 1 second per second. There's nothing strange in my own local frame of reference. You don't notice like any length dilations or mass dilations, as long as you're along for the ride. Oh, Earth Twin looking through a telescope, maybe a different story. According to special theory of relativity, all laws of nature are the same in so we're looking for reference frames that move at constant speeds. That's also called an inertial frame of reference, inertial frame of reference. Okay. Now, once you accelerate, that's what gets you up to a different speed. Like Earth Twin and Rocket Twin did both start out based on the same planet, right? And then Rocket Twin had to accelerate up to a fast speed. Anything that's oscillating, well, oscillating also involves acceleration. Right? Okay, so yeah, we're looking for inertial frame of reference, which is either at rest or constant speed. Clocks on a spaceship moving very fast appear to run slow when viewed from Earth, but only from Earth, right? So um, Earth twin looking through the telescope says, like, bro, what's going on with your clock? It's running super slow. But rocket twin inside the rocket doesn't perceive anything strange in his own local environment. And maybe rocket twin looks through a telescope back at Earth and says, well, like, bro, your clock is running fast, right? But yeah, as long as you're along for the ride, right, then in your own local environment, you see 1 second per second. Atomy bones. Ada, Fred, Stephen, and Kent. You're actually looking into the past when you look at what's technically the correct answer. Technically correct. Okay, yeah, there you go. All right. So both of you. Now, starlight would definitely be true. Do you guys know how much time it takes for sunlight to reach the Earth? Yeah, there you go. A little over 8 minutes. Yeah. So already there, like that's 8 minutes into the past. Like if the sun exploded, we wouldn't know for 8 minutes, right? The further you look into space, like distant stars, it's like many light years away. Means you're looking like years into the past, right? That Hubble Deep Field up there, you can see Hubble Deep Field, right? Those galaxies, well, that's as they looked like billions of years ago, right? So that's all definitely past, right? But really, anything you're looking at, like if you guys look at me right now, it might be like a tiny fraction of a second into the past. So yeah, there you go. Kind of a trick question, sort of, I guess, right? But yeah, maybe philosophical. Think deep on that one. When you approach a light source, the wavelength of light emitted appears what? Uh, short. Okay. Um, all right. I did want to draw this one out. So most of you guys got that, but do you guys remember the Doppler effect? The Doppler effect. So um, let's have a well, I might draw a car in motion, but let's have like a galaxy in motion. How about that? Right. Let's say a couple of galaxies are moving relative to each other. Right, so I got a galaxy here. So draw like a hurricane, right? Or just like a galaxy. And let's say this is like the Milky Way. And let's have this be Andromeda. How about that? Andromeda. Right. Now, Andromeda galaxy is actually headed towards the Milky Way galaxy, right? And the fact that it's in motion towards the Milky Way galaxy, like through space, right? It's sending out light waves in all directions. But if it's in motion, isn't it kind of catching up to the very light waves that's sending out as it's headed towards the Milky Way? Right? You guys remember this Doppler shift? Right. So if you look at this wavelength of light, it's be really short, and on the other side, it'd be like elongated. Right? So this is the Doppler effect, right? Doppler effect. Right? Now, uh, if the wavelength appears shorter, and we're talking about light in this case, there's a term for that. Does anybody remember the term for that? It's called red shifting or blue shifting. Hold on. What guys? What's a longer wavelength of what's a shorter wavelength of light? Red or blue? Shorter wavelength is like the blue. Yeah. So this is like blue shifting. Okay. Versus if you were on the other side of this galaxy and it's going away from you, that'd be called red shifting. Okay. Now, if you're thinking, wait, aren't other galaxies red shifted? That's true for almost all other galaxies compared to us in the universe, right? Andromeda is one of the weird exceptions that it's headed towards us. It's like in our galaxy cluster. Right? Yeah, if it's headed towards you, the wavelength appears shorter. Right? This blue shifted. Right? In fact, the further away galaxies are from us, because of how the universe expands, they're moving faster away from us, and they're more and more redshifted. So you can actually take advantage of that redshifting to calculate right, how fast they're moving away from us and how far away they are. All right. In some reference frame in the universe, you are traveling close to the speed of light. Yeah, that would be true, right? Hey, how about that Hubble deep field right there, right? Right. Those galaxies are actually moving away from us, technically faster than the speed of light. Now, this is a really weird concept because wait, I thought nothing can move faster than the speed of light, right? So those galaxies moving away from us, um, faster than the speed of light, not because they're moving through space, like that would be the violation of relativity, but because space is actually expanding between us and them, right? Like faster than light would be able to travel. Right? Yeah, astronomy can get really weird with like how light can reach you and yada yada. But yeah, there you go. And so yeah, um, to someone in the universe, it appears that we're moving close to the speed of light or at the speed of light. All right, we got Got to be bone swag, Fred on fire, got Stephen and Kent leading the pack halfway through. A friend is riding on the back of a truck that's going away from you at 25 kilometers an hour. As the truck passes, your friend throws the ball at 55 kilometers an hour relative to her. So that's towards you. Right? How fast is the ball going relative to you? Give you guys a hint. This is not Einstein relativity. This is just plain Newtonian relativity. Uh, only a couple guys got that. Right. Here, let's switch back over because this is a last semester concept. This question is kind of out of place in this section. I mean, it's a relativity question, but it's Newtonian relativity, right? So there's nothing fancy going on here. We don't worry about like the speed of light or the perception of that or anything like that. No, we're just back to first semester physics. Right? So here's this truck going at 25 kilometers per hour away from you. Right? Now that's the velocity of the truck relative to the ground. Right? Then this person's going to throw this ball at 55 kilometers an hour towards you the other way. Now that's how fast they can throw the ball. So that's the ball. Sorry, not relative to the ground. Oops, my bad. Relative to the truck, right? The ball to the truck, relative to the truck, right? And maybe I should even throw on a negative sign because it's opposite directions. You guys see opposite directions? Right? Now, do you guys remember adding vectors tip to tail? So you said, what's the velocity of these things, right? The truck relative to the ground is 25 kilometers an hour this way. This is V truck to the ground. Right? It's 25 kilometers an hour that way. Right? Then we got V ball to truck. Okay. So this is 25 kilometers an hour. Okay. This is 55 kilometers an hour in the opposite direction. Okay. So I connect it going backwards. Okay. Then you guys remember the resultant? The resultant is go from the tail of the first one to the tip of the last one. Okay, you guys see that? And that would be V ball to ground. Okay. And that's going to be your 30 kilometers per hour. Maybe you could even say negative, but I guess the speed would be 30, right? I guess that you just very simply subtract the two vectors. Right. So that's the answer we're looking for. Right. So V ball to ground, we write it bigger, just is 30. That's like the opposite value, right? Kilometers per hour. Okay. Right. That's good. All right. So there you go. That's just plain Newtonian relativity. So nothing to do with Einstein, really. All right, Stephen to the top spot. To a person inside a spaceship moving close to the speed of light, a meter stick held horizontally inside the ship looks. Nice. Yeah, just the same as always. So the idea here is, of course, if you're in the frame of reference of the spaceship, then you don't notice anything strange about the spaceship. Right? You don't notice any weird length contractions or dilations. You don't notice any time dilations. Okay? So if you're in your own local environment, okay? looks the same. Nice. You guys remember that? All right. We got Stephen on fire. That's the top spot. To calculate how much rest energy an object contains, you multiply how much energy. Yeah, nice. Mass times the speed of light squared. That's how you interpret that equation, E equals mc squared. That's what that means, right? We calculated one of those yesterday, and we're going to do another calculation with that today. Okay. So yeah, you guys did better on that than my last class too. Yeah. So E energy, um, E energy equals m mass times c the speed of light squared. Right? The speed of light is being squared. Okay. E equals mc squared. You guys know that's the energy of nuclear reactions. Okay. All right, I've got Swag, Fred, Dr. Bones, Kent, and Steven. Objects accelerated to relativistic speeds appear from Earth Twin's reference frame. Oh, one winner, one winner. Right. So the opposite of the red is true. The opposite of the yellow is true. Yeah, but the blue one, gain momentum. Right. So flip over and let's look at these relativity expressions. Here we go. Right here, right here. Okay. Guys remember these? So, uh, so the deal with like living longer or shorter time, guys. Which twin got old? Earth twin or rocket twin? Earth twin got old, right? So from Earth twin's frame of reference, and that's the premise of the question. Rocket twin actually appears to like stay young longer, right? That's like the opposite of whatever that answer choice said, right? Uh, how about um, in length, like same thing, right here, guys. If you speed up at a relativistic speed, let's do example number. What if v is some significant fraction of c? So this fraction could be between 0 and 1. Isn't that true? Okay. You guys ready to follow this logic? Okay. You guys got your brains turned on? Okay. Guys, 1 minus anything between 0 and 1. Let's make up something. Let's say 0.5. Let's say this piece comes out to 0.5. Guys, what is 1 minus 0.5? 0.5. Okay. The square root of 0.5, is that also between 0 and 1? Should be. Square root of 0.5. Yeah, it's like 0.707. Right? In fact, this whole square root is always going to be bounded between 0 and 1. It goes low 0 as high as 1. So if you start off with any rest length and you multiply by something between 0 and 1, does that make you longer or shorter? Shorter. It's got to be shorter, right? Which was the opposite of that answer choice. But how about gain momentum, right? So momentum is mass times velocity. I mean, I guess velocity is going up, momentum's going up anyway. But there's this added effect of or I should say maybe a multiplicative effect of this dilation. So if you divide by something that's bounded between 0 and 1, that always makes it what, larger or smaller? Larger. Like what is 10 divided by 0.5, for example? Ooh, that's like 20, right? So it makes it bigger. And you might also remember this right here. Like gaining momentum. Maybe you could even say like gaining momentum that Newton wouldn't have predicted, right? Like Isaac Newton says, yeah, as you go faster, you gain momentum, but Isaac Newton said that would be like a linear relationship. Uh, Einstein says, no, actually, you have to divide by this Lorentz factor, so it gets even bigger. Okay, heads up towards infinity. You guys remember that? All right. Who got that? Oh, Fred got that. All right. Woman standing on the ground sees a rocket ship move past her at 95% the speed of light. Compared to the rocket at rest, she would see the rocket's length as Okay, half you guys follow that. Okay, let's flip back over here and look at this this length contraction. Yeah, right here. Okay, so let's run the same thing that I just said. Okay. Let's say the rocket was like 10 meters long, so 10 meters, right? And it flies by like 95% of the speed of light. Let's try that. What is 95% of the speed of light compared to the speed of light? It's like 95%, right? And that's being squared, right? So it's like 0.9, a little bit. Right? 1 minus 0.9, that's like that. And you take the square root of that, right? So with the exact number that you were given, this whole square root comes out to be like 0.31. Guys, what is okay, 0.31? Isn't that like 31%? What is 31% of the original 10 meters? And that'd be like 3 meters, right? Which means you're getting shorter, right? You guys remember yesterday the train paradox? The train goes through the tunnel in the mountain. And if you're in the reference frame of the mountain, doesn't the train appear to get shorter so that it completely enclosed by the mountain tunnel? You guys remember that? Right? That's the same question. All right. Got Swag moving up. Got Kent and Steven in the lead. When an object is pushed to relativistic speeds, its momentum is measured to be. Okay. Um, guys, all these posters I'm showing you guys do know they're hanging right here on the ceiling, right? Right? Guys, look at this one right here. Here, let me flip my screen over so that anybody watching this on video later. Okay. Okay. So this is the equation version of it, but let's look at the graph version of the same thing, which, okay, the equation's also there. We're talking about this. So for conventional speeds, momentum is, you could just call it mass times velocity, just like we did last semester. We were always dealing with like collisions like down here. Remember that? But relativistic speed, we're talking about like a significant fraction of speed of light. Let's say like 90% speed of light here, right? Do you guys see that this red line is always above this green dash line? So Einstein's version of momentum is always more than Newtonian momentum, right? For relativistic speeds. You guys see that? Right. The equation version backs it up because this whole Lorentz factor, the square root, is bounded between 0 and 1. Any value divided by a decimal between 0 and 1 is always going to blow up bigger, right? You see that? Right? All right, moving up. Relativity equations for time, length, and momentum hold true for all right, nice. Yeah. Relativistic scenarios, but also everyday scenarios. Okay. So there's a science principle embedded in this called the correspondence principle. Let me flip over and talk about this a bit. This is going to show up a little bit later today when we're solving some of those other puzzles. Okay. So it goes like this. Um, if there's anything relativistic, obviously you can just use these equations as they're listed. But what if something's like a non-relativistic speed? Okay, so this fraction would be pretty close to 0%. Let's look at time dilation, for example. Guys, if your v is non-relativistic, then v squared on c squared is just pretty close to 0, right? So we can just treat it as 0. It's what is 1 minus 0? 1. What's the square root of 1? 1. What is t naught divided by 1? T naught. Oh, and look at there. Earth twin time, Earth twins time and rocket twins time, they match. Right? So everybody agrees on how much time matches, or how much time has passed, as long as it's non-relativistic. And if it is relativistic, then you just apply that Lorentz factor also. Okay. So the idea of correspondence principle is if you come up with some new theory that's supposed to replace some old theory, like Einstein did with Newtonian mechanics, okay, then, or did to Newtonian mechanics, then your new theory has to also cover the basis of what the old theory was already good at explaining. All right, more points. If you were to travel at speeds close to the speed of light, you would notice what? Yeah, there you go. None of the above, right? So you don't notice anything in your own frame of reference, right? Nice. Right. Got swag on fire. Stephen the lead. Uh, if Einstein's equations of special relativity are valid, they must. Yeah, nice. That's the correspondence principle all over again, right? So they do have to um, also verify Newtonian mechanics for non-relativistic cases. Right? Yeah, there you go. All the above. Right, nice, nice. Right. And for the win, 10-meter long spear thrown at a relativistic speed through a 10-meter long pipe. Now, 10 meters and 10 meters is, let's say, when both were at rest. Okay. But now it's been thrown at relativistic speed. When the spear passes through the pipe, ooh, okay. You guys did pretty good with that one. Great, nice. Actually, you guys are really good at that. Okay. So let me go over this one because this one takes some thinking. But this is the same as the train paradox that you guys saw yesterday. Remember the train going through the tunnel? Does the train extend out the tunnel or is it completely covered by the tunnel? Well, it depends on your frame of reference. So here I've got a pipe and a spear. You guys see the pipe and the spear? Right. And at rest, okay, 10 meters, all fine and good. Now we're going to throw this spear through the pipe at a relativistic speed. Well, from the frame of reference of the pipe, like if you're standing at rest with the pipe and the spear goes through at a relativistic speed, you're going to say that the spear got shorter and is completely covered by the pipe. Okay. But what if you're along for the ride with the spear? So from the frame of reference of uh, the spear is always 10 meters long, but the pipe would actually get shorter. Okay. So it's relativistic effect. All right, let's switch back over here one more time. Let's grab the winners to the podium. All right, with the bronze, Kent. With the silver, swag, and the gold, Steven. All right, and for runners up, we got to my bones and Fred. All right, nice job, guys. Nice job. On that. All right, so let's do, whoops, that.